Okay, perfect. Hi everyone, so welcome to this presentation on how to build secure contract, and in particular how to fuzz like a pro. So who are we? My name is Josselin Feist, with me is Natalie Chin. So we are both security researchers at 12 Bits. If you don't know us, we are a company where we specialize in high-end security technology. We work on blockchain, but we also work on other areas. We have expertise in cloud-native application or in cryptography. One thing that makes us different from other companies, I think, is that we are always trying to apply the latest program analysis technique into our daily job. And as a result, we have built a lot of tools. You might know Slither, which is a static analyzer for smart contract. Echidna, we are going to talk about it today. Tiller, which is a static analyzer for algorand smart contract. We have also a static analyzer for KO smart contract. We have also a fuzzer for KO. So we have a lot of tools that we have built over the years. All these tools are open source, all these tools are like free to use. But today we are going to focus in particular on fuzzing. So we are going to discuss what is fuzzing, how to use it efficiently, and how to use it in your daily job. At the end of the presentation, the goal is going to be for you to have some intuition on how to apply fuzzing in your daily job as a developer or as an auditor. You can find the slide of the presentation here. Right now it's on a pull request, and soon it's going to be on the master branch. So 12 bits publication, it's simple. Okay, the first question we are going to ask ourselves is how to find bugs. Let's say you have this piece of code. So you have like 10 lines of code, more or less. What this code does is that it allows anyone to buy some token. It has a function, a public function to buy, and it has some function that is going to check that you are providing enough ether. You don't need to spend too much time on this. You don't need to try to understand it. The question is more, you are giving this piece of code, what can you do to check if there is a bug? What can you do to check if there is something wrong going on here? Basically, you have 4 techniques at your arsenal. The first one is unit test. I'm assuming everyone is aware of how unit test works. You can do manual analysis, you can do fully automated analysis, and you can do semi-automated analysis. The first one, unit test, you basically create a test case to check like some specific value of your system. Unit tests are good, and you should use unit tests, but usually you're going to cover like the happy paths, like the paths that are going to lead to good behavior. You are going most likely to miss all the cases that can lead to vulnerability or critical issue. We actually have data from our past experience with working with clients that shows that there is no correlation between having good unit test and the likelihood of having a high severity issue in the code base, which is an interesting result. Just an example of unit test, nothing new here. The second technique that you can use is manual review. So you can go line by line in your piece of code and try to see if there is something wrong, try to see if something can be abused by an attacker. This is difficult, this is time consuming, and it's going to require some specific skills. You need to understand how to think as an attacker, you need to be aware of all the class of possible bugs that can happen in a code base. Usually to do manual review, you're going to ask a security firm such as 12 bits or other to perform this type of analysis. Mostly because, as I mentioned, it's time consuming and it requires like a specific set of skills. The next technique that you can use to catch some of the bugs are fully automated analysis. So here you have a tool, you're going to run the tool on your program, and you're going to try to see if there is a bug. For example, there is Slither, and it's going to catch the most common type of issue, like reentrancy and stuff like that. It's really good to catch some specific type of bug. It's really good to kind of catch the common type of bugs, but it's not going to be able to find more like subtle bug, more bug related to the logic of the system. Here you have an example of Slither. So Slither is a static analyzer, and we have integration with the GitHub code scanning page, such as a developer, you can add it for free in your workflow, and every time you do a commit, every time you do a pull request, the code is going to try to find like the most common vulnerability. Reentrancy, uncheck call, and so on. The last class of techniques that you can use is called semi-automated analysis. So here you're going to use a tool to check if there is a bug in your system, but instead of looking for common vulnerability, you are going to help the tool to provide some form of specification of what your code is supposed to do. And here you're going to look for bug related to the logic or bug related to the more in-depth application of what you are trying to do. One technique is called property-based testing, and with Echidna, and it's what we're going to talk about today.
Yeah, so I'm going to go into property-based testing, what it is, and particularly what it is in relation to Echidna. So basically, from Echidna's point of view, when you're fuzzing, you're essentially, it would be like you were typing on a keyboard, trying to throw random inputs at your smart contract. What happens when you call a certain function with inputs that aren't expected? What happens, unlike unit testing, you're specifying maybe a certain variable or a certain number. With fuzzing, you're essentially going to be tapping at the keyboard, except that it's all within the fuzzer. So fuzzing is pretty well established within traditional security software, and for a lot of the times, these fuzzers, when they're used in those contexts, are checking whether a contract or whether a code base would crash. Are crashes possible within this context that you're running it in? But smart contracts don't really have crashes. So with Echidna, we're not going to be looking for smart contract crashes. We're looking for, we're thinking of this on a different angle and thinking what are properties that you want to hold true within the code base. And from a developer standpoint, what needs to be true in a code base. It's basically like unit testing on steroids. So to start with, what is actually required in order to do invariant testing? Well, you need to know what invariant is. You need to know in terms of your code base, and it's going to change for every code base, what needs to hold true. And Echidna, this is where Echidna comes in, because we're going to be able to call these smart contracts with with defined invariants. And we often use these in audits, and we see this used in very mature code bases. So this isn't a replacement for unit testing. This is, you have unit testing and you have fuzzing. So you can get the duality. So one example is, is when you have a token, one invariant would be that a user balance should never exceed total supply. If it ever does exceed total supply, then you know there's a bug somewhere in your smart contract. Maybe it's arithmetic, maybe it's likely it's arithmetic, but access controls, for example. Once you have that property, then you need to actually convert that into code. So this specific example is, we're defining a function called Echidna balance of total supply. And what Echidna is going to do is look for all the functions that are prefixed with Echidna, and specifically ones that return the Boolean, and it'll essentially determine whether there might be scenarios in which the value of the balance of the sender is less than equal to total supply. So this looks very similar to what you might write in a unit test, except in this specific case, Echidna is now going to generate and call the smart contract from a series of different addresses to see whether this invariant may break. So from an Echidna standpoint, unlike unit testing, where you need to specify what are the incoming arguments, with Echidna, we have this smart contract code, and for this example, it's really just an ERC20 token. This is a simplified example. Of course, it has, in this example, total supply, balances, and a transfer function. And the invariant that we're specifying is that the balance of the message.sender is less than equal to total supply. So from Echidna's standpoint, it's going to determine throwing random inputs within message.sender and calling different functions like the transfer function. Is it possible that this invariant ever breaks? So this requires a bit of a paradigm shift compared to unit testing, because we need to think about, in terms of this entire system architecture, what is required of the system in order for it not to break. So for this example, this is the transfer function. It's essentially going to decrease the balance of the message.sender and then increase the balance of 2. It's from the inputs, it's going to get the 2 address as well as the value. And when we put this through Echidna with the property, we can define this test token as inheritance through using the token contract. And from when we initialize this contract, it's going to be initialized so that the Echidna caller, which is the contract address that's going to be calling this contract, gets started with an initial balance. So once we actually define these Echidna tests, we can now define this property as using Echidna to test the balance, making sure that the balance is now less than or equal to their initial balance. So once we run Echidna, it's going to now determine that if we call the transfer function with the 0 address and a value of 1, this specific input set is going to now break this invariant. So from a triage point of view, Echidna will provide all of the inputs that are required to break this invariant. Now, so this is a very simplified example. A token contract is one that's relatively easy to reason about because the standards are defined, the variables are defined. We know exactly what's expected to happen in a token contract. Now, that raises a really good question of what are invariants within more complex code bases, and how do we actually start thinking about invariants in terms of larger contracts and larger and more complex contracts. So to start with, in order to even find invariants and start finding them, we need to start small and start iterating over what are possible invariants that we can now build on top of. So from a developer standpoint, and from our experience on audits as well, is defining in a certain piece of code what is the code expected to do. And this is the baseline. That we need to know what the code does in order to even define what property should be holding true. Once we get that, and we can get that through documentation, through talking to developers, understanding use cases, understanding the context in which functions or contracts are used, then we can actually start running them and writing them into Solidity. And this process is much easier said than done, because we need to also make sure that Echidna isn't going to specifically choose. It's going to essentially, it's like the cat on the keyboard. It's just going to randomly generate these inputs. And so we need to be very careful with what are your preconditions that you want to specify in terms of if an invariant is actually going to hold, defining all your preconditions and postconditions, and then finally running Echidna. So if these invariants are actually broken, and Echidna finds a test property that fails, then that's where the manual investigation, you need to go in, need to determine why is it failing. Is it because your invariant was wrong? And that requires a whole level of discussion of, is it something that's within your contract, or is it something that's within your system architecture, or is it in the translation between the invariant from English into code? So to start with, you really need to sit and think about what your contract is actually supposed to do. You need to really determine from the experience of really combining the experience of project teams who are building the code and really understanding expectations. The easiest way that I've found is really to just write down what the invariant is, what is expected of the system in English, and then you can start to really change and convert that into code. So as an example, math libraries are one that's easier to reason about because there are expectations that you expect math libraries to hold. For example, 1 + 2 is always equal to 2 + 1. If any of these properties don't actually hold, then you know that there's a bug in your smart contract. In the same way that you can test a math library, then you can test other libraries in the same way. And going back to the token example as well, one example for total supply is that no user should ever have a balance that exceeds total supply. that goes back to if this is ever possible, then there is a bug in this contract. And we can also start to reason about what are the expectations for other functions as well. For example, if you're transferring tokens to another user, you always expect that the sender's balance is going to decrease and that the receiver's balance is going to increase. If there are any changes and that doesn't actually hold, then we know that there's something wrong within that token contract. And similarly, we can reason about expectations of what would happen if you don't actually have enough funds. If you have insufficient funds, then you should never be able to transfer balance. If that is ever possible within a token contract, then you know there's also a bug. Once you get into understanding what are the expectations from the high-level point of view, then you can really start to think about how would you actually test this in practice? How would you write the Echidna properties in order to really be able to determine whether, use Echidna to determine whether it's exploitable? So there's really two different methods to do this. One is function level invariant, and this is going back to the example with the expectations for arithmetic, and this is stateless. So you can essentially, you can get Echidna to, for example, call a contract that adds two numbers and then adds the same two numbers in the different order and just making sure that they're equivalent. The other system level invariant is going back to what would happen if you're using Echidna to test something like total supply. So for function level invariance, it's always going to be inheriting the target. We're going to be creating the test function that essentially wraps the contract or the function that we want to test, and then we're using an assertion statement just to make sure that they're actually equivalent. So this specific Echidna test is essentially Echidna is now going to generate random values for these two uints, and any property in which, or any set of values in which this assert statement is false, Echidna would raise an error. The other type of Echidna usage is through system level invariance. And there's two different ways to do it. One is if you have a relatively simpler setup within these contracts that you actually just use like Echidna to deploy the entire system. This would mean that pretty much any time you're iterating over your code, then you can run the contract and deploy the new version within your constructor. And Echidna, what it will do is be able to explore all of your publicly available functions and determine whether there are variations of functions that it can call in order to break the invariance that you've set. The other option is especially true of very complex code bases that have many contracts that work together. You can also use either your unit test framework or your deployment scripts to deploy the set of contracts on essentially a local version of your blockchain, and then Echidna can start to fuzz on top of that. So if you have a very complex setup, then you can essentially run your deployments, get it running on Atheno, and Echidna will start to generate transactions on top of the code of the state of the blockchain after those deployments have been run. So for this specific example, this is a system level invariant, and this is a very similar example to the previous. And basically, Echidna is going to determine whether there are any cases in which this assertion will fail. So I'll pass it.
Before I go further, is there any questions? Yeah.
When you generate the input, is it really pure random input? And if yes, how do you get sufficient coverage?
Okay. That's a really good question. So it's not purely random. Echidna is going to kind of collect the value at one times and is going to use them from time to time. And there are also some heuristic, like it's going to favor edge case, 0, 1, 2, max uint, -1, -2, and so on. So it's more or less random, but there is some kind of smart heuristic in it.
Do you analyze the code in advance? Do you extract a constant from the code?
Yeah, exactly. We actually use Slitter or static analyzer to extract the constant, extract a couple of arithmetic operation, and we feed this to the fuzzer. And what was the second question?
No, that's it.
Oh, okay.
Quick question.
Yeah.
From more of like a DevOps perspective, do you guys plan to essentially enable this to be triggered through like something like GitHub Actions, and then you guys have your own infrastructure with Ganache or whatever you guys are using to then kind of facilitate the automatic deployment of contracts against a testnet?
So technically it runs on its own version of the VM, so there is like a local kind of blockchain, and we have a GitHub action for it. So you can configure it and just let it run. On GitHub action, there's discussion on how much time you want the fuzzer to run. You can let it run for like 10 minutes, you can let it run for 2 days. For 2 days, not going to work well with GitHub action. So it depends on your setup.
Seems like a nice business.
Well, actually the tool is free, so. Okay, oh. Yeah. The fuzzing itself is done on the bytecode. But for the, to get the constant before fuzzing, it's done on the source code. Yes. But then we run like opcode per opcode. Okay, so really the approach is to start simple. You think about the invariant in English, you convert them into solidity, and you iterate. Now the question is where to start, which function to start. Should you focus on the contract? Should you focus on multiple functions? Should you explore different approach? And when you have the code base, you don't know where the bugs are, right? Otherwise, you will not do that. So you have like a code base, you don't know where are the bugs. You basically have two approaches. The first one is coverage-based, where you are trying to cover as many functions as possible, not necessarily in depth, but just to cover as many different behavior from the system. The second approach is to go and focus on one or two components and go in depth, going in depth in the sense of trying to write as many invariants as possible for this specific component. And you can iterate. You can start by spending maybe 1 day as a code coverage. You're going to try to cover as many functions as possible with really simple invariants. After 1 day, when you have some intuition and some understanding of the system, you can focus on a specific component. Maybe a math library, maybe some bookkeeping, maybe something a bit more complex. And you go in depth. You're trying to kind of write as many invariants for this specific function or component as you can think. At some point, you will be to a position where you don't have any idea anymore, or you're writing invariants that are exactly the same and you are not progressing. Then you can just switch back and go back and forth like this. There is no right or wrong approach. It's really a matter of building your own experience, building your own expertise, and based on your intuition with respect to your understanding of the code base, obviously. Something which is really important, and we're going to repeat it again and again, start simple. If the first invariant that you are writing leads to a bug, there is something wrong in your process. Basically, like the first 10, 15 invariants that you are going to write should not lead to any bug, because they should be simple and they should kind of highlight really things that should already be true within the code base. By starting simple, it's going to help you to have a better understanding of how to write the fuzzer or write property with the fuzzer. Maybe start having some kind of initialization, maybe more complex system invariant, and you can build on top of that. Once you have really simple invariant, you can start to think about composition. You can start to think about function relation. Are there functions that should behave more or less the same? We took the example of the token. If you have a transfer and a transfer from, if you call transfer from where the from is the sender itself, should they behave the same? Yes, no? Is transfer additive-like? Additive-like in the sense that if I want to transfer 20 tokens, can I do 2 calls to transfer with 10 and 10? Should it behave the same? Should both execution be equivalent? Spoiler, no. I won't explain why it's not equivalent. I will let you think about it. But going through this exercise of trying to understand the expected behavior of the system and what should be true and what should not be true, it's kind of a process that you are going to go through, and it's going to help you as you are going to build your expertise on this. And yeah, from our experience, even if you don't use Echidna at all, if you just stay at the English level and just write your invariant as like a list of 20, 30, 40 things that the system should do, it will already help you. It's already going to be a huge step forward with respect to the maturity of your code base. If you use Echidna or any other tool, it's going to be even better, but just by starting by thinking about invariant and having this shift in the paradigm in the way you are building contract is going to help you a lot. And actually doing audits sometimes where we are like, okay, what the system is supposed to do, like what are the invariants? Just by writing some invariants, we realize that some are obviously wrong and broken, even before running Echidna. So this is really like a powerful tool in the way we are kind of thinking about the code base. Okay, if we take back the first example. So again, here I have a function that can buy. It can buy 10 tokens per 1 ether, and you have a function that is going to check if you provided enough ether with respect to the number of tokens you want to buy. You have 2 functions. The first one, buy, is stateful. It's going to mean something, so you have like the state of the function, of the contract that is going to change. The second one is stateless. It's just taking some parameter, and if everything goes wrong, it just returns. So here you can start with the second one. It's easier, you don't have to do any initialization, you don't have to mint any token, and you can just focus on that. What invariant? So here, the function basically takes some token, takes some amount of ether, do some computation, and try to see if you provide enough money. One invariant here is that if you provide 0 ether, the second parameter must be 0. Otherwise, it means that you can provide, I want to buy 1 token, 10 token, 100 token, and if I provide 0 ether, this should revert. Otherwise, you get token for free, basically. Something which is interesting here is that this is an invariant, but you can write it without even understanding what's the arithmetic here. Like here, the arithmetic is simple, but you could have like really complex formula. You could have like things related to Uniswap or like complex arithmetic. You don't even need to understand it. You can just by thinking about how this function should behave, you can write invariants. Here's an example of invariant. So I am checking that the number of tokens I want to receive is above 0. I'm calling this function, and here I provide 0 to the second parameter. So I'm calling this function by saying the number of tokens I want to have is above 0, but I'm providing 0 ether. And here I'm just saying that assert false because this should never be reached. This function reverts. So basically, if during the execution I can reach this path, the invariant is broken. I've done something that should not have happened. And if you run this with Echidna, it's going to say, oh, I managed to break this invariant, and I call the function with 1. Why is that? Do you have any idea? Yeah, exactly. Like here, you are doing the number of tokens divided by 10 because you want to buy per 1 ether 10 token, and if you ask to build to mint less than 10, this is going to run to 0, and you basically get the token for free. So here again, you write an invariant, you don't even think about the formula, you don't even think about what it does, and you manage to find the bugs, which is pretty nice, I think. Any question? Okay. Let's talk about other tools. So Echidna is not the only tool that allows us to do semi-automated analysis. There are a couple of additional fuzzers out there. There is one in DAP, one in Bonnie, one in Foundry. This framework might be easier to use on the first step. They might allow you to quickly add some simple tests with fuzzing because they are within the compilation framework, so you might be more used to it. However, they are not as powerful as Echidna. We have been working on Echidna for, I think, 5 years now, and we have been using it in countless of audits. We are using it basically in 3/3 of our audit. So yes, I'm not going to have the same number of features, not going to be as smart in the exploration. The second kind of categories of techniques that use semi-automated analysis are formal method-based approach. So you have Mantic, KVM, etc., and so on. So these techniques are going to be more or less the same idea, like the user is going to define an invariant, the user is going to define like the specification of the contract, and the tool is going to use formal method to check if the invariant holds. This technique have one kind of benefit over fuzzing is that they can give you guarantees, they can give you proof that the bug is there or not. However, in practice, all these tools are difficult to use. They require some specific knowledge. They require like years of expertise in program analysis to use them correctly. So basically, like if you have 1 week, like you are developing your system and you want to spend 1 week to improve the confidence of your code base, the amount of kind of confidence you are going to gain by using fuzzing in comparison to using one of these techniques is just not going to be on the same scale. Like to use this technique, if you have like months, you will be able to use them. If you have 1 week, you won't be able. This is a quote from the CEO of runtime verification, so the people building KVM, is basically saying that if you want to use formal methods to check and to verify your contract, you need to have 9 times the resource for development. And this is from the team building this tool. So as a developer, it might even be like significantly higher. So they are nice to use, but they are really costly. Echidna has a couple of unique advantages, I think. We have a couple of additional features that are not there in most of the other tools. For example, Echidna can give you a summary of gas consumption using fuzzing. So basically, it's just going to call all the functions randomly. It's going to give you an idea of what are the transactions that consume the most gas. If you are looking to kind of tune with optimization of your system and you want to find some edge case, if you want to find some place where running the code might be really costly and you haven't think about it, using fuzzing is like a nice kind of way of doing it. It can do differential phasing. So differential phasing is basically the same idea, but instead of comparing a properties, you are going to compare 2 implementations of the same things. For example, if you have 2 contracts, version 1 and version 2, and version 2 is just a refactoring of your code base, but it should be at the same, you can use differential phasing to actually check that they are the same. It works with any compilation framework. Ardart, Truffle, Brownie, Foundry, whatever you are using, Echidna will work on top of it. We have different APIs. In the example, we saw a couple of examples where using the Boolean property, where you define a property and the function should return a Boolean, or assertion, you define with an assert. Or there is another mode for using with the DAP test and Foundry mode, which is slightly different, but more or less the same idea. Again, it's free and open source. So you can just use it and there is no limitation. Okay, so today we saw Echidna, which is a smart contract fuzzer. If you want to learn more about it, we actually have tutorial in building secure contract. In this repository, you will find a lot of additional guidelines on how to improve the quality of your code base, not just for fuzzing, but using additional tools and additional guidance. For example, we have a token integration checklist. If you want to integrate with arbitrary token, what are the things you should be aware of? Regarding Echidna, again, start simple. Try to write invariants that you know are not going to lead to any issue, but they are going to help you to build on top of it, and they are going to help you to have like an iterative approach. Start with English, then Solidity, then Echidna, and loop over it. Also, we are hiring. So we are hiring both security consultant and apprentice. So we have an apprenticeship program, which is a 3-month program where we train people to become Solidity auditor in the company. We have been running the program for more than a year now, and we ended up hiring everyone. So if you're interested in this topic, let me know. Final word, your mission after this presentation is to try Echidna either on one of your code base or on some of the code you have. And let us know how it goes. Let us know how writing invariant goes, and let us know what's the difficult part and what we could improve to make your life easier. Any question?
So I'd like to hear your approach about how do you write invariants. As I see it, there are two ways, either which is interface-based or implementation-based. So on the first approach, you can just look in the interface without implementation and think for yourself what the properties should be. And the other one is just when you just focus on the implementation itself, and then you restrict yourself to what the function actually does. So what is your approach on that?
That's a really good question. I think it goes back to having an approach, code coverage or behavior coverage. Like the interface is going to be a bit more code coverage, where you don't necessarily go in depth into what the system is supposed to do. You're just taking as like a black box. This is what it's supposed to do. Let's write an invariant. Then you can go one step further and really try to understand the actual behavior of the system, the actual, I don't know, if you have like a 5 line of arithmetics, what this arithmetic are doing, what they should be leading to, and then you go a bit more in depth. So again, it's really a matter of going back and forth between both approaches, where sometimes you want to just go briefly over the different interface, and sometimes you want to go like in depth. Both are important, and it's going to depend on your code base and your approach and your understanding of it. No. Yeah. Oh.
Yeah, I just want to add quickly, sometimes it's useful to look at the interface first, because then you can start talking to your developers and just making sure that those assumptions that you have on your interface are correct first, until you start digging deeper into the implementation, and then just making sure that your high-level assumptions are correct first. So sometimes we do often bounce between the two, and I think that's probably the best use of time, because then we can also, there are cases in which you might look at invariant and say, yes, this looks correct, but once you really start thinking about how is it being used in a system and getting that context, that it's actually correct but with more preconditions than you initially thought.
And it's kind of like thinking about fuzzing as unit test on steroid. When you're going to build your unit test, it's the same. Are you going to just build like regression test? Are you going to build unit test? It's going to depend on your approach.
Hello. In the YAML configuration, you have like the test limit and the
yeah.
the length of simulations that you do. Usually, what number do you use there? I start with, I don't know,
Okay, that's a really good question. So the question is about the configuration of Echidna. When you run Echidna, you can configure some stuff, and there is 2 parameters. One parameter is the number of tests you want to do, like number of input you want to generate. Do you want to test, like if you have a function, do you want to test a function with 10, 100, 1 million inputs before like before Echidna stop? The second parameter is the sequence length. This is only important for system invariant. The sequence length is going to be when you start Echidna, you are at sequence 0. Echidna is going to make multiple transactions, 1, 2, 3, 4, whatever, is going to go in depth into the program, and at some point it's going to reset. So the sequence length is basically, yeah, is basically the number of calls before Echidna reset. For the number itself, answer is it depends. If you are looking at function invariant, the sequence length can be like 1, basically, because you don't care if it resets. It's going to be a bit slower if you put it too small because of internals, like when you reset a blockchain, you have some variable you have to reset. For the first parameter, the number of tests you want to do, this really depends on how much confidence you want to have about the code base. So I don't have like a concrete answer for that, but it's basically going to depend on the budget you want to put in the exploration. Do you want it to run it for 1 hour? Do you want to run it for 2 days? That's basically it.
But you have some cases that you run for 2 days.
Yeah, like for like we sometimes we run it for like a weekend or something like that. We have a second repo. It's called should come back, hopefully. Yeah, we have another repo. It's called Echidna powered, and basically what it does, it's also open source. It's going to parallelize Echidna runs so that you can run it on on the cloud basically, and you can run it with multiple processor, and it's going to share the input generation. So if you have like a large machine with a lot of processor, a lot of memory, you can also not run it over like 2 days. You can run it over 5 hours, but in parallel.
How can you control the fuzzing domain range so that, say, you want to test only numbers under like 100K, because that would potentially accelerate the process?
That's a really good question. So how can we kind of help the fuzzer to not explore any value and only focus on specific one? The really simple way of doing it is to add precondition. Like here you say it should be greater than 0. However, this is not the best approach because the fuzzer is still going to generate input. Here it's just 0, so there's just one value that is going to be rejected. But let's say if you want to have this value between, I don't know, 20 and 25. One way to do this is to use modulo. So in building secure contract, you will find kind of a pattern and tips to implement that. But basically the idea is that here you could write this where the number of token you want is equal to the input, and you use modulo to create a range between the value. It would make more sense with the example, but it's like a programming pattern to reduce the range of the value. Like basically, Echidna is going to generate any uint, and locally you can reduce this. That make sense?
And the corollary, like, is it possible to run Echidna on a wide range, but don't let it fail on the first failing assertion? Like, you let it compute all the successful and failed sets, and you could like somehow draw a conclusion on what kind of values it just failed for.
So you mean like if you have multiple assertion and you want to...
I just don't want Echidna to like fail on the first assertion. I just want it to run, compute the whole thing, and just analyze the data set that at the end.
That's a good question. I don't think we can do that out of the box. You can probably tweak by commenting the asset and stuff like that. We have a corpus we use in Echidna, so if you run it without any assertion, it's going to generate a corpus of inputs, so all the input to explore that it used to explore, and then you can reuse this by adding assertion. So it's not out of the box, but kind of, if that makes sense.
Complex code base with multiple contracts and stateful invariants. Like, do you have any tips to like get there on very specific scenarios, like when there's a lot of contracts, a lot of states, and so on?
So we have this additional tool. As I mentioned, we have a lot of tools. Where is it? Yeah, I don't remember where is it in the slide, but it's called Echidna, and basically it's a tool that is going to allow you to run your unit test and seed the fuzzing with unit test. So if you have a unit test that calls 5 different contracts first, Echidna can reuse this information and start the fuzzing after it. So if you want to, if you have a complex system, you need to have like a lot of different initialization. Maybe you need to want to do a couple of first swap, or you want to do something like that. We can, but it's a bit more complex, but we can with it.
Is this compatible with Foundry or any kind of test, or?
Oh, it's compatible with any tests that can run with Ganache. So if it's not compatible with Foundry, we can probably add it pretty quickly. So the question is regarding if we can support main and fork. Not directly, because the issue is that basically Echidna is going to create his own virtual machine. You have to repeat the transaction from mainnet to seed it. Like you cannot connect directly to like an entry point or something like that. It's something we're working on, but it's a bit more difficult. If you can replay, yeah. But what we need is a transaction in Ganache. So it's not like the initial state of Ganache, it's really like the transaction sent to Ganache. So we can replay anything we can see as transaction, but we cannot take an initial state at the moment. Does it make sense? Yeah.
I use an external contract within my code. Do you have any way to fuzz into it? Like with this static analysis?
Okay, so we do support out-of-the-box multiple contracts. If you have the source code, you can just if here you have like an external call and the contract is deployed, Echidna is going to work out of the box. Like Echidna supports multiple contracts, and it's needed for like system invariant, because like any like common contract is going to a system is going to have multiple contracts.
Yeah, and just I guess it's a bit of a follow-up to a previous question. With the testing, when you have a bunch of inputs and it creates an error, like it fails an assert or something, you found, like you've broken an invariant, it will then like change the inputs and do it again, or does the testing sort of stop there?
Oh,
I was just
yeah.
I'm not sure.
So there is a technique which is called shrinking, because basically, like let's say Echidna found a set of transactions to break the invariant, but maybe a lot of transactions within this set are useless. Maybe just call randomly some function and everything. So once Echidna is found an invariant which is broken with a set of transactions, is going to try to reduce the transaction size so that you have kind of a meaningful call.
And then it continues, and if another
and it continues to
broken,
the other one, yeah.
And then you just get a report at the end of all that. Yeah. Okay.
Yeah,
Thanks.
and you have like a live report with respect with like the clean interface, like yeah, I think I have like a screenshot. Yeah, okay, like here it's the end, but it's running. Yeah.
So doesn't mean that, because you earlier mentioned that you need the transaction to be monitored in order to like apply. It doesn't mean that doesn't work for read only transactions where you don't actually change the state, where you just like if you have a pure function reading a state and computing an output.
So if you just have like, if you send like within your unit test or deployment a read function, a read transaction, it's still going to use it to seed the information. So it's still useful.
See the interaction. So it's not.
You basically just need transaction input. And if the transaction does nothing, change nothing, it might still be valuable for the fuzzer, because maybe you are calling like a getter with, I don't know, an index or a value, whatever. And this might be useful to explore later on some path.
Thank you.
Okay, any additional question? Who is going to try Echidna? Okay. Yeah, and if you have any question, we are here for the week, so don't hesitate to ping us.